who's a graduate student at MIT, working with Tom Layton, although he seems to do more work by himself than with Tom. And he's done a number of studies, algorithmic results over his short career. So he's going to tell us about one of them solving a very long-term open problem.
Thanks for the flattering introduction. So this is based on joint work with Adam Kalai and Greg Valiant. So the first thing I'd like to do is I'd like to tell you what a mixture of Gaussians is. That's the first question we should answer. So the quick answer is a mixture of Gaussians is a distribution on Rn. In fact, more precisely, we can generate a random sample from a mixture of two Gaussians.
Wow. Sorry, it's a big distraction.
Okay.
Huge chunk of ice just
All right, so we can generate a random sample from a mixture of two Gaussians as follows. We take a coin which is biased, which is heads with probability W1, and is tails with the remaining probability W2, and we flip it. And if the coin comes up heads, then we take a random sample from the first Gaussian and we output it. And if instead the coin comes up tails, then we take a random sample from the second Gaussian and we output it. So in this way, we can generate a random sample from a mixture of two Gaussians. And in fact, the density function of this distribution is just the convex combination of the density functions of the two constituent Gaussians. So now that we know what a mixture of Gaussians is, the next question I should answer is why are they important? And in order to answer this question, let me tell a story that dates back to Carl Pearson in 1894. So Pearson was a very famous statistician who was interested in evolution. In fact, there was a particular species of crab called the Naples crab that inhabited the region around him. So what Pearson did was he took many samples from this crab population and he measured some physical characteristic. In his case, he measured the ratio of the height of the crab divided by the circumference of its head, and he plotted the frequency of occurrence of different values. But the density function that he got surprised him because it wasn't the Gaussian. In fact, the density function wasn't even symmetric around its maximum value. So he was quite puzzled, but what he offered as an explanation was that the Naples crab was not composed of one species of crab, but rather two, and that the density function could be explained as a mixture of two Gaussians. So in fact, he set about the algorithmic problem of given random samples from what he thought was a mixture of two Gaussians, trying to estimate the parameters of a mixture of two Gaussians that could explain his data. So in fact, I'm going to go into his approach in a little bit of detail because actually some of the ideas and the techniques will actually be relevant to some of the results that I'll present at the end of the talk. And Pearson set about this problem of trying to determine the parameters of the mixture of two Gaussians. And of course, in order to learn the parameters of the mixture of two Gaussians in one dimension, what we really need to learn are just the values for 5 free variables. We need to learn the mixing weight, which of course fixes W2, which is just 1 minus W1. We need to learn the mean and variance of the first Gaussian and the mean and variance of the second Gaussian.
Is it good that there's a unique decomposition?
It turns out that there is. So I'll discuss that a little bit more towards the end. In fact, I'll give you an alternative proof of that. But one way to sort of see that is just based on if you go far enough out in the tails, what will define the density function in the exterior regions of the tail will be the largest variance. So you can sort of factorize that out and figure out the rest of the distribution. In any case, Pearson's approach was based on the method of moments. So in fact, let me give a notational definition. Well, I'll call the expected value of x to the r when x is sampled from f sub I of x, the rth raw moment of f sub I of x. So Pearson's first observation was actually that the rth raw moment of a Gaussian f sub I of x is actually, it's a polynomial in its unknown parameters. It's a polynomial in its mean and its standard deviation. In fact, it's a degree r polynomial, and for those of you who know what Hermite polynomials are, it's essentially a Hermite polynomial. And this will be an important polynomial for our purposes, so I'll give it a special name. I'll call it m sub r of mu I sigma I squared. But now, as I mentioned, Pearson's approach was through the method of moments. So if our approach to learning the parameters is through the method of moments, we have to be able to answer this question. what would knowing the moments of a mixture of two Gaussians f of x, what would that tell us about the underlying parameters? Okay, so in fact, we can expand it. If we take the rth raw moment of a mixture of two Gaussians f of x, then in fact, the resulting rth raw moment is just the convex combination of the rth raw moments of the two constituent Gaussians, where each term is weighted proportional to the mixing weights of the two Gaussians. And so in fact, if we knew this value, the scalar value for what the rth raw moment of f of x, which is a mixture of two Gaussians, if we knew this value, then what we would have is we'd have a polynomial constraint on the underlying parameters. So the answer is knowing an rth raw moment tells us a polynomial constraint. In fact, but we won't have access to the rth raw moments of f of x. Instead, what we have access to are random samples from f of x. So instead, we'll have to come up with some estimate for the rth raw moment, and that's exactly what Pearson did. We'll use the natural empirical moment of the corresponding set of samples. We take some set of samples. We'll define the empirical rth raw moment as just the expected value of x to the r over the entire sample set. And this, in general, will just be, it'll be a reasonable approximation for the rth raw moment, depending on how many samples we take, but it will certainly have some error inevitably. But so now I can explain Pearson's idea, which is called the sixth moment test. So his idea was take many samples from the underlying crab population and use these samples to compute the rth raw moments for r from 1 to 6. And what he did was he used the first 5 raw moments, each of which then gives us a polynomial constraint on the underlying parameters. Well, he used that set of the first 5 raw moments to set up a system of 5 polynomial equations. And the intuition is just that we have 5 unknowns, so one would hope that having 5 polynomial equations is enough to narrow the solution set down to some finite set. And in fact, what he did was remarkable. I mean, this was way before computers, obviously. He solved the system by hand. And he got all the simultaneous roots of this system of equations. So he got some candidate set of parameters that maybe could explain the data. And each set in this list is a setting, is a simultaneous setting for each of the 5 variables, so that if those were the values that each of these variables were set to, then they would explain the data in terms of the first 5 moments. Unfortunately, he had more than one possible set of solutions here. He had more than one list of parameters, more than one candidate parameter set in his list. So he had to determine this problem of how do you figure out which among the parameter set in this list most probably explains the data. And what he developed was a heuristic, but it'll still be important because we'll analyze it rigorously later. Now, some of the sets of parameters in here were clearly not the right answer. Some of them had negative mixing weights, some of them had negative variances. So those were clearly not the answers he was looking for, and he threw those out. But there was still more than one possible set of parameters that could explain the data based on the first 5 moments. So in fact, his idea then was to use the 6th moment as a tiebreaker. Each of these candidate sets of parameters, it yields some analytic prediction for what the 6th moment would be if the parameters actually were according to that set of parameters. So all he did was for each of the remaining sets of plausible explanations, he figured out a prediction, and he compared them to the empirically observed 6th moment, and he accepted whichever one was the closest. So this is called Pearson's 6th moment test, and I want to stress that this is actually just a heuristic. There are a number of problems with actually showing that this actually does recover the parameters of the underlying mixture. For example, we don't even know if step 2 is well defined in any sense because we're using the empirical moments and not the true moments. So these aren't exactly polynomial constraints on the true parameters. So a priori, we don't even know if this system of polynomial equations has any simultaneous roots, and we can continue with this procedure. That turns out not to be the biggest problem. The biggest problem is really just showing that such procedures actually recover estimates which are close to the true values. And yep.
Can't you just check it against the data and see if it fits?
So a priori, you don't know if there aren't 2 different sets of parameters which create distributions which are exponentially close to each other based on, suppose the parameters are different by epsilon.
That was my previous question about uniqueness.
So the uniqueness doesn't imply that there's a polynomial that if the parameters are epsilon different, that you'll be able to notice it, because if you had to go all the way out into the tails to notice the difference between the distributions, that would take exponentially many samples even to get a sample from that. And that's exactly why overcoming this problem will be the main sort of barrier to the talk, is that you need to do something non-trivial besides just going out in the tails. But that's a great question. Does that answer the question? OK, perfect. So really, we're after trying to understand, can we get rigorous guarantees for actually recovering the parameters of a mixture of Gaussians? In fact, Pearson asked some variant of this question, which was really, how does noise in the empirical moments translate to noise in the derived parameter set? Instead, we can focus on the contrapositive of this question, which is a more algorithmic way to look at it, which is if we want some desired accuracy of epsilon, we want to learn the parameters within some additive epsilon. How many samples do we need to take to do so? Is it polynomial in 1 over epsilon, or is it exponential? So I'll return to this question at the end, and I'll actually show a way to analyze Pearson, a modification of Pearson's sixth moment test. But for now, I'd like to move on and explain at least the results that I'm going to present in this talk in a broader picture. But hopefully with this as an introduction, it's easy to see why Gaussian mixture models have so many applications in different fields like physics, biology, geology, and the social sciences. It's because in each of these fields, some random process of interest can be explained as a convex combination of 2 or more Gaussian processes. In fact, whenever Gaussian mixture models arise in these fields, a very natural question is to try and estimate the parameters of the mixture. And in fact, once we have good additive estimates, say, of the parameters, then we can perform a number of algorithmic and classification tasks. For example, for a mixture of 2 Gaussians, if we knew good additive estimates of the parameters, then we could do things like take in a random sample from the distribution. We could compute a good estimate for the posterior distribution, for which cluster is likely to have generated the sample. OK? And so in fact, because this problem arises in so many different fields, there are many widely deployed, widely successful heuristics. For example, the EM algorithm is a very popular choice, which is a local search heuristic that searches over likelihood in terms of explaining the data. Unfortunately, such algorithms don't necessarily return the true parameters in the mixture. In fact, even for the EM algorithm, it's been empirically observed that it can take a very long time even just to converge, even for mixtures of 2 Gaussians in 1 dimension. Forget that it's not even converging necessarily to the true parameters. So instead, the question that I'm going to focus on is the question as Dasgupta introduced this problem to theoretical computer science and asked the question, can we provably recover the parameters? And can we do so efficiently? So in fact, I'd like to survey, before getting into our results, I'd like to survey some of the work done in theoretical computer science on this topic. And in order to do so, let me just introduce one more notational definition. I'll say that d of f comma g is the statistical distance between f and g. And this is just if you take the density functions of the distribution f and the density function of the distribution g, and you measure half of the L1 distance between these 2 functions, f of x and g of x. That's the statistical distance. Are there any questions? All right, so when Dasgupta introduced this problem to theoretical computer science, and here I'll denote n as the dimension of the mixture of Gaussians, so the dimension of the data, and k as the number of components in a mixture of Gaussians. Well, when Dasgupta introduced this question to theoretical computer science, he showed that for well-separated mixtures of spherical Gaussians, one provably could recover the parameters. In fact, what he required was that the centers of the Gaussians be separated by at least square root of n times the largest variance in any direction. So the components really needed to be very far separated. And the separation condition was later improved by Dasgupta and Shulman to n to the 1/4. And subsequently, Aurora and Kannan used isoparametric inequalities to generalize this to mixtures of non-spherical Gaussians. And unfortunately, for the techniques used in these 3 papers, this actually was the barrier to those techniques. All of these papers were based on the idea that if your data was extremely separated in high dimensions, if you project onto a randomly chosen low-dimensional subspace, the data will still be somewhat separated in that low-dimensional subspace. And if your data is somewhat separated in low-dimensional subspace, then what you can do is you can efficiently find a good clustering, which, given many samples from your mixture, accurately clusters every single sample based on which component generated it. Then all I have to do is spit out and the empirical mean or empirical covariance of that cluster, and that'll be a good estimate for the corresponding component. So actually, in order to break this barrier, Vempala and Wang and Aklioptis McSherry, they chose the low-dimensional subspace more intelligently. So instead of choosing it uniformly at random, their idea was that if you instead took the largest principal components based on some small sample of the data, that this would actually isolate a low-dimensional subspace that contained most of the interesting information in terms of learning the mixture. So in this way, they were actually able to get a separation condition which depended on the number of components as opposed to the intrinsic dimensionality of the data. And the more recent work of Brubaker and Vempala, they actually generalized all of these results. But the first thing that they noticed was that for this example, which they termed the parallel pancakes example for obvious reasons, that all the previous approaches failed. Because in fact, the separation between the two Gaussians is much smaller than the largest variance of any Gaussian in any direction. Nevertheless, in this case, there's still a half space that separates the two, so that almost all of one component is contained on one side, almost all of the other component is contained on the other side. So in this case, too, they were able to provably recover the parameters. This was based on what they called isotropic PCA. It was based on the idea that now you could put it into isotropic position and essentially compress this down so that you could get back into these frameworks, but exactly. So, but the main point that I'm trying to get across is that each of these papers had varying assumptions on the mixture in order to provably recover the parameters. But at the very least, each of these papers needed to assume that the statistical distance between the two components is close to 1. And the reason for that is because all of these approaches were based on clustering. They're based on the idea take many samples from your mixture and then be able to accurately cluster every single one based on which component generated it, and then output the empirical mean and covariance. The problem is, what happens if the statistical distance between my two components isn't close to 1? What if it's, say, 1/2? If these two components overlap in roughly half of their mass, then actually very quickly, when we take random samples, we encounter a sample which we don't know which component generated it, even if you told us what the actual mixture was. So in fact, for statistical distance, say 1/2, these approaches provably can't work. Is that clear? Any questions? So in fact, we can ask a stronger question. We don't need to think that the only way to learning the parameters is through clustering. We could ask, what happens if we just want to learn the parameters as opposed to doing clustering? In fact, we can ask an even stronger question. Can we learn the parameters when the statistical distance between the two components is close to 0 as opposed to close to 1? So what if they overlap almost entirely as opposed to only non-negligibly? And so actually the answer to this question will be yes, it turns out, and it'll be based on exploiting the algebraic structure of mixtures of Gaussians, as opposed to, say, the geometric structure which was used in a lot of the isoparametric inequality proofs of previous papers. So let me introduce now a goal, which will be the learning goal that I'll be interested in this talk. In fact, it'll be even stronger than just learning the distribution correctly. I'll want to learn the distribution on a component-by-component basis. So what I want to learn is I want to learn some mixture of two Gaussians. It's no surprise. And I'll never know which of my components should be labeled component 1 and which one should be labeled component 2. The labeling is arbitrary. So at best, I can hope that there's some matching between the components in my mixture and the true components, so that across this pairing, we get both the mixing weights and the Gaussians right. For example, what if the matching matched 1 to 1 and 2 to 2? Then what we'd require is that we learn f hat so that W1 is additively close to W1 hat, and the Gaussian F1 is statistically close to the Gaussian F1 hat. And so in this case, we'll say that this mixture f hat is epsilon close to f, if it satisfies this condition, if it's close on a component-by-component basis. So if this is our learning goal, then the first question to ask is, when can we even hope to learn epsilon close estimates? And it turns out there'll be two trivial cases where we can't hope to do this, but these will be the only cases. So I claim if one of the mixing weights, for example, is 0, then we could never hope to learn, no matter how many samples we take, we could never hope to learn an epsilon close estimate, because we never sample from F1, no matter how many samples we take from F. So in fact, F1 to us looks arbitrary, so we could never hope to get it right. And the other remaining case is, what if the two Gaussians were the same? What if the statistical distance between F1 and F2 was 0? Then in this case, no matter what the choice of the mixing weights are, well, a random sample from F looks the same. So in fact, we'd never be able to tell if the mixing weights are split 50-50 or 1 minus epsilon and epsilon. So in this case, too, we cannot learn an epsilon close estimate. And in general, our goal will somehow to learn an epsilon close estimate in, say, poly and 1 over epsilon samples. So in general, we'll need to assume some quantitative lower bound for each of the mixing weights and for the statistical distance between the two Gaussians, because we'll need to assume that given, say, 1 over epsilon samples, we have a good chance of getting at least one sample from each component and at least one sample from the non-overlap region between the two Gaussians. This is provably minimal assumptions. But we'll say that a mixture of Gaussians, F, is epsilon statistically learnable if each mixing weight is at least epsilon, and the pairwise statistical distance between the two components is at least epsilon. So now I can state our main result, which is actually just given Oracle access to any epsilon statistically learnable mixture of, say, two Gaussians, and I'll explain our results for k later, then there is an algorithm which learns an epsilon close estimate to F. And in fact, its running time and data requirements are polynomial in 1 over epsilon, n, which is the dimension of the data, and 1 over delta. And these are provably minimal assumptions for learning an epsilon close estimate. You need to assume some lower bound on the statistical learnability. And actually, previous estimators, as I mentioned, they required weighting for samples all the way out in the tails. So they were all exponential unless you made larger assumptions about the separation between the two Gaussians. So the outline for the talk, I'm going to state our results for k Gaussians, and then I'm actually going to get into some of the, the proof behind this. So very quickly, I'm just going to, yep.
So a question about the previous slide. So
Yep.
the failure probability is 1 minus delta, and the running time of data are probably delta or log over delta?
Yeah, I mean, it should be log 1 over delta, but right now the way we proved it was 1 over delta for this, but it should be. You're right. So what about mixtures of k Gaussians? And so we can define an analogous notion of epsilon statistical learnability. So here we would again need to assume each mixing weight is lower bounded by epsilon, and now all pairwise statistical distances are at least epsilon. So now, and we can define an analogous definition of our learning goal. We want to learn some mixture f hat, which is epsilon close to f if there's some pairing from R components to the true components, so that again, across the pairing, we get the mixing weights right within an additive epsilon, and we get the Gaussians right. So the statistical distance between fi and f hat pi of I is at most epsilon. So for k Gaussians, again, given Oracle access to an epsilon statistically learnable mixture of k Gaussians, it turns out there is an algorithm which learns an epsilon close estimate. And its running time are polynomial in 1 over epsilon n and 1 over delta. And someone should be complaining right now because there's no k that shows up. It turns out that the degree of this polynomial in our algorithm depends on k. But the funny thing is that actually, if you want to learn an epsilon close estimate, it turns out that you need to depend exponentially on k. So this is a very strong learning goal when you want to get the components, when you want to get the mixture right on a component-by-component basis, as opposed to just getting the density function right. So it turns out that even for sort of one-dimensional problems, there are two different mixtures of k Gaussians, which even though they're not good estimates for each other, their distributions are exponentially close in k to each other. So just in order to distinguish between those two cases, you need exponentially many samples. So when you want to learn such a strong learning goal, you need to depend exponentially on k. But as far as I know, if you just want to learn a good distribution, f hat, I don't know of any lower bound which really depends intrinsically on k, or really should tell you that it shouldn't depend polynomially on k as well. And so I can tell you one quick corollary of this. It turns out that you can get proper polynomial time density estimation for mixtures of Gaussians. So what I mean by that is even though you have to assume here in this theorem that the mixture of k-Gaussians is epsilon statistically learnable, this lower bound on the mixing weights and the pairwise statistical distance, what you could do if you're given an arbitrary mixture of k-Gaussians, what you could do instead is you could run this algorithm and assume some lower bound, or you could, if the intuition is that if you're not epsilon statistically learnable, say there's one component which has very small mixing weight, then you could essentially ignore it, and you can make this intuition more rigorous, and you can show that actually you can do density estimation without making any assumptions on the epsilon statistical learnability of the mixture. For example, for two Gaussians, if you violate that condition, either one of the mixing weights is very small, or the two Gaussians are statistically close. So in that case, if you just took enough samples, well, the mixture would still look like one Gaussian to you, so you could just spit out that empirical mean and variance, and that would be a good estimate. So now I'd like to actually get into some of the intuition behind the proof. As I mentioned, this will mainly be based on exploiting the algebraic structure of mixtures of Gaussians. And one frequently asked question that I get asked a lot is, what about additive guarantees? So right now I've been focusing on the statistical guarantee of epsilon closeness. And one could ask, what does that really tell us in terms of learning the parameters within some additive accuracy? Well, you can't, in general, give good additive guarantees without assuming some normalization for the data. Because if you gave me an algorithm which always learned within an additive epsilon the parameters, before I give you the data, I could just scale it up by a large constant factor, and then you'd have to give me a much more accurate estimate, additively, for my original mixture. So in fact, the point is that you need to define some normalization of the data to prevent you from just scaling it up, to actually be able to define, to be able to give an algorithm which gives additive guarantees. And this notion of normalization will be what's called isotropic position. So what I'll describe in the bulk of the talk will be getting additive guarantees when you assume that the mixture of two Gaussians is in isotropic position. So a distribution f of x is said to be in isotropic position if, first of all, the expected value of x sampled from f of x, so this is a vector because it's a multi-dimensional distribution, well, if this is the all-zero vector first, so if its mean is 0 in all directions. And additionally, we require that the variance is 1 in every direction. So if you choose any unit vector u, the variance along that direction, if you project your mixture, is 1. So this sounds like a very strong condition the first time you see it. Getting variance 1 in all directions, not just, say, the axis-aligned directions. But actually, it turns out, and this just follows from the Cholesky decomposition, that actually if you give me any distribution f of x, it turns out there is an affine transformation t, so that this transformation t places f of x in exactly isotropic position. And let me just give one example to explain the intuition. So here's a mixture of two Gaussians, which is not in isotropic position, in fact, because the variance along the y-axis is certainly larger than the variance along the x-axis. So these can't both be 1, so this is not in isotropic position. But in this case, what we could do is we could stretch the data out along the x-axis. And in this case, we actually could make it isotropic position. And in general, you might need to compose this with rotations, but any distribution can be put in isotropic position. Are there any questions? OK, so as I mentioned, I want to focus on giving additive guarantees when it's in isotropic position. So suppose we're given this epsilon statistically learnable mixture of two Gaussians. Now let's assume for the time being, for simplicity, that the mixture is even given to us in a form which is exactly in isotropic position, let's say. Now what I want to do is I want to learn some mixture of two Gaussians so that there's some pairing, so that across this pairing I get the mixing weights right, but also the norm of the difference in the means is at most epsilon, and the Frobenius norm of the difference in the covariance matrices is also at most epsilon. So this is the mean of the high-dimensional mean of the ith Gaussian. OK? And so now I can at least tell you a sketch of the proof, and then we'll go into details on this. The idea is to actually reduce the problem down to one dimension. So we'll consider a series of projections down to one dimension. So when we project a mixture of two Gaussians onto a direction, we get a univariate mixture of two Gaussians. And we're going to be able to run a univariate learning algorithm on each of those one-dimensional projections. The key is that when we learn good estimates for the projection of the parameters that we get when we project the data onto one dimension, that actually gives us constraints on the higher dimensional parameters of the mixture of two Gaussians. So we could hope to learn the parameters in many different one-dimensional projections in such a way that we can stitch together these estimates and get some system of equations which we can then back solve to get good estimates in high dimensions. This is the idea. So let me go more into detail on each of these points. But so a simple claim, which I'm sure many of you are familiar with, is just that if you take a Gaussian in high dimensions and you project it onto a direction, it's a univariate Gaussian. In fact, when you project the high-dimensional Gaussian, the univariate Gaussian that you get is the projection of its mean onto R, the direction, and the variance that you get is the quadratic form of R on the covariance matrix. Seems reasonable. So in fact, the point is that if for one Gaussian, say, we learned what this scalar value was when we projected it onto R, and we learned what this scalar value was when we projected it onto R, and we knew the direction R, that would give us a system, that would give us linear constraints on the high-dimensional parameters. Right? Because this is just, if R is fixed, this is a linear equation in sigma 1. And we're going to encounter a number of problems with this approach as I've sketched it. So let me give one notational definition that will explain the first problem that we encounter. I'll say that the parameter distance between two univariate Gaussians is the difference, the absolute value of the difference in the means, plus the absolute value of the difference in the variances. And I'll call that the parameter distance. So the first problem that we're going to encounter is if our idea is to take the mixture of two Gaussians in isotropic position and project it onto a direction. What happens when we project it onto a direction R and the parameter distance between the two univariate Gaussians? We project F1 onto R, we project F2 onto R. What if the two univariate Gaussians we get are extremely close in parameter distance? This would be a problem if that were true, because we want to run our univariate learning algorithm on that projected univariate mixture of two Gaussians. So if these two had extremely close parameter distance, we might have to run our univariate algorithm extremely fine precision to even see the differences between those two Gaussians. That would be a big problem then. So the way that we're going to get around this is actually be able to show that with high probability, that doesn't happen. In fact, if you take an epsilon statistically learnable mixture of two Gaussians and it's in isotropic position, the parameter distance between the projections of the two components is non-negligibly large, is at least some polynomial in epsilon and 1 over n. So it can't be exponentially small, and we can still hope to run our univariate learning algorithm with this precision and be able to tell the difference between the two Gaussians. So we'd be OK so far. And let me give you the formal statement. So F is in isotropic position. It's very important that it be in isotropic position, because one can think of isotropic position as being the sort of it weights different directions when you project randomly in such a way that you actually can separate the two Gaussians. So suppose F is in isotropic position and it's epsilon statistically learnable. Then with probabilities 1 minus delta over a randomly chosen direction, the parameter distance between the two univariate Gaussians that we get in the projection is non-negligible. It's at least some fixed polynomial in epsilon and delta and 1 over n. And whatever this quantity is, I'll call it epsilon 3. And this will actually give you a hint as to how many problems we're going to need to solve to be able to solve the high-dimensional problem.
Is dp just the statistical distance again?
No, this is the parameter distance. So it's the absolute value of the difference in the means plus the absolute value of the difference in the variances. So what I want to sketch is actually just the intuition for this. So there'll be two cases. Suppose we're given our mixture of two Gaussians. This isn't in isotropic position. I've drawn it, but let's pretend for now. Well, we can draw a vector u, which connects the means of these two different components. The first claim is just if we know how a random vector projects. So if u is non-negligible in its magnitude, then in fact, when we project onto a direction r, the difference in means that we get first is just, first of all, it's the projection of u onto R. So in fact, if u is non-negligible, if it's some fixed polynomial in epsilon and 1 over n and in delta, then in fact, when we project it down, we'll just divide the magnitude by square root of n with high probability. So in the case where the means are slightly separated, we're done. We already know that these two will have different parameter distance, just by virtue of them having a difference in their means. Of course, this need not happen. The vector u, in fact, could be 0. So here is a mixture of two Gaussians, which is certainly epsilon statistically learnable because the overlap between the two Gaussians is bounded away from 1. And it is an isotropic position. This time I've drawn it correctly. But now what happens is that the intuition is that if the vector u is 0, let's say, then the only way that f1 and f2 can have at least epsilon statistical distance from each other is if in a typical direction their variances look different. And that's the intuition, is that now in the case where the means are, let's say, the same, then it has to be the case that when I choose on a randomly chosen direction r, that the differences now in their parameters of these two projections will be owed to their difference in variances. So that's at least how the sketch of the isotropic projection lemma goes. Oh, yep.
So the epsilon to the fifth, that comes from the second portion of the argument? Or is it,
Yeah. I mean, so it comes from balancing the two sides against each other first, because you're going to assume some lower bound on u otherwise. And the way, I mean, the intuition for how you can actually go about proving isotropic projection lemma, it's a little bit technical to actually do it. But the idea is that things like the KL divergence, if the statistical distance between the two Gaussians is lower bounded, the KL divergence is also lower bounded. Right, and then the KL divergence is actually very well defined between two different Gaussians. It'll just be some statement based on their covariance matrices and the relative eigenvalues in different directions. And then what you can get is that sort of gives you a way to sort of, when the variances are different in some direction, that'll tell you that when you project onto that direction, that'll sort of be the reason why they have different variances. So the proof just goes through writing down what the KL divergences and analyzing that.
So the point is that the difference in variances is like it's a relative eigenvalue. It's not like the
Perfect. Yep. Exactly. And then you also get these extra terms in the KL divergence based on the differences in the means, and compared to what the variance is in these different directions. So in the case where you have upper bounds on the difference in the means, then you can bound how much you throw away from that term, and then you still have some lower bound on what their statistical distance is, and hence the KL.
This actually says it in most directions.
Yes. Yeah. Exactly. I mean, yeah. And then you can, yeah. I mean, I can describe it in a little bit more detail later, but there'll be a lot more to the sketch of the proof anyways. So let me get into that. So now let's encounter our second problem. We only used up epsilon 3. We have much more epsilons to use up. So now we're going to encounter another problem, which is, suppose we do all this. Suppose we project the data onto direction r, and we learn some good estimate f hat of r. And suppose we project the data onto direction s, and we learn some estimate f hat of s. These are both mixtures of two Gaussians that we've gotten from running our univariate learning algorithm. Well, the problem is the first component, say, of f hat r, that's a Gaussian. It's a univariate Gaussian. Its parameters, its mean and its covariance, these scalar values, they yield constraints on the high-dimensional parameters of one of the two Gaussians. Same with f hat 1 of s. Its parameters yield constraints on one of the two high-dimensional Gaussians. How do we know that they yield constraints on the same high-dimensional Gaussian? So at the end of the day, when we set up this system of linear equations, we have to make sure that it's well defined, that we've only put in valid constraints on it. Yeah, how do we know that they yield constraints on the same Gaussian? So in fact, just to illustrate the problem, we don't know when we project onto this direction r, we don't know what the pairing is, so that they've come from the same Gaussian. And this we're going to get around by a cheat. The idea,
Can you just run over all possibilities?
then I would lose, see, in general, I need at least, let's say theta of n squared, different univariate estimates, because there's n squared different variables in the covariance matrix. So I don't want to run over all, pairings. for that, right? But we'll cheat anyways. Let's cheat a different way. The idea is that if we choose directions close enough, then pairing becomes easy. And here, actually, the notion of close enough will depend on the isotropic projection lemma. More specifically, it'll depend on what this epsilon3 quantity is that we got out. So here's the idea. Suppose the directions r and s are close to each other. They're within some quantity epsilon2, where epsilon2 we think of as much, much smaller than epsilon3. But it's still, polynomial in epsilon3, so it's not, it's only polynomially smaller. The idea is now, we still make the same assumptions. F is an isotropic position and is epsilon statistically learnable. Then it turns out that if you take, say, F1 and you project it onto R, whatever that univariate Gaussian is, its parameter distance from F1's projection on S isn't too large. It's at most, epsilon2 over epsilon, which we can make much smaller than, say, epsilon3. And to illustrate this, the point is just, now the point is, suppose I project on some direction r. I know from the isotropic projection lemma that their parameter distance between the two components is non-negligible. It's at least epsilon3. Let's suppose that the reason that they have different parameters is because they have different means. So suppose the means were separated. Now the point is that as we sweep from direction r to direction s, the means change continuously. In fact, so if we can bound how much these means change, in this case, then if they were already separated by epsilon3, if they can't move more than epsilon3, then they can't have crossed. So in fact, now in this case, pairing becomes easy, because whichever one has the smaller mean on this direction s is also the one that has the smaller mean on this direction r. And in the other case, what if the reason that they had different parameter distances was because they had different variances? Suppose their variances were different by epsilon3. Well, again, in this case, as we sweep the direction continuously from r to s, then the means again change continuously. And again, if we can bound how much the means change, then pairing in this case also becomes easy, because whichever one has the higher variance in direction s is the same as the one that has the larger variance in direction r.
So you choose r and s randomly, and then you sort of walk from one to the other?
So what you can do is you can choose essentially just one root direction, which you choose at random, and then the isotropic projection lemma holds. And I'll go over this later anyways. So they're separated by epsilon3. Then you can choose many neighboring directions, which are close by. And in each of those, you can pair them to which one they correspond to in the root direction. So you only need the isotropic projection lemma to hold once. And then after that, just the fact that they can't change too much will be enough in these different directions. But I'll go over that when I put all the pieces together. OK, so now let's encounter the last high-dimensional problem, which is now let's suppose we've done all that. And for each high-dimensional Gaussian, suppose we have many, we have in many different directions r, we have estimates for the univariate parameters when we project on that direction. So we have many linear constraints on this one Gaussian's high-dimensional parameters. We still have the problem that inevitably, I haven't told you how we do the univariate learning algorithm, and I'm going to get to that at the very end. I haven't told you how we do that, but invariably, there will be errors in the univariate learning algorithm. We won't learn the exact parameters. So when we set up the system of equations, how do the errors in our univariate estimate translate to errors in the high-dimensional parameter set when we back-solve this system of equations? Another way to put this is, in the language of linear algebra, is what's the condition number of this system of equations? And in general, we can't hope for the condition number to, say, be constant, because you know what? A lot of these directions are very redundant, in fact, right? So if we're choosing many directions which are within epsilon2 of each other, then in fact, the information is very correlated across these different directions. But the key point, and this I'm not even going to get into how we prove it, but the point is that the condition number is polynomially bounded. It's at most, say, n over epsilon2 squared. Because the point now is that if we want to learn in the univariate learning algorithm to some error epsilon1, then what's our error going to be in high dimensions? It'll be epsilon1 times this condition number. So if we choose epsilon1 small enough, now much smaller than epsilon2, but still polynomially bounded, then we actually can learn estimates in high dimensions, which are accurate to within some additive epsilon. So that's the idea. And let me now piece together all these different pieces right now, and I still haven't gotten into the univariate learning algorithm. But now we choose some randomly chosen direction r, and owing to the isotropic projection lemma, we know that in fact the parameter distance between the two components will be non-negligible, will be at least epsilon 3. Let me assume in this figure for simplicity that the reason they're different is their difference in means, and the case will be analogous in the other example as well. But so we know the difference in their means is at least epsilon 3. Now we choose many different directions s, say n squared of them, which are within some quantity epsilon 2. They're very close to the root direction. Well, we know that the difference in means is lower bounded by, say, epsilon 3 over 3, that their means haven't crossed first, that whichever Gaussian has smaller mean here is the same as the Gaussian that has smaller mean here. And now what we can do is we can run our univariate learning algorithm, which I've asserted exists, and I'll get into that later. And we learn to some additive accuracy epsilon 1. And same for the projection on the other directions. And now we can perform pairing. And so now for each Gaussian, we actually do have estimates which are within an additive epsilon 1 of the true values, which then we set up a system of equations. And actually, when we back solve it, it will get us good estimates in high dimensions. And same for the other Gaussian. Are there any questions? All right. So now what I've described is this additive isotropic algorithm. And what I really promised you was that, that we could get statistical guarantees. So in fact, additive guarantees, getting the parameters right additively, is not enough to say that we have statistical guarantees as well. For example, consider this mixture of two Gaussians, f1 and f2, the two solid Gaussians. Well, if we learn the dashed Gaussians, then this is a mixture of, this is an estimate which is additively close to the true mixture. Because the parameter distances are close here and the parameter distances are close here. But this isn't a good statistical estimate because f2 hat is not statistically close to f2. But it turns out that the only way that you can get additively close guarantees without getting good statistical guarantees already. So the only way that this situation can happen is if you have some direction of very small variance. So in general, based on if you assume lower bounds on the variances, you can use upper bounds on the parameter distance to get upper bounds on the statistical distance. So this is the only way that this can happen. But the point is that when this happens, we've still made progress. Because even though we've learned estimates which are only additively close and they're not statistically close, well, we know we're in trouble. Because we found this Gaussian f2 hat, which has a very small variance. And this f2 hat is additively close to the true Gaussian f2. So we know that f2 has very small variance. And now we can use this mixture of two Gaussians that we've learned to cluster the data. Because here in this case, we can take a direction of small variance for f2. And we can project the data onto that direction. And what does the mixture of two Gaussians look like when we project on that direction? Well, f2 has very small variance in that direction. So in fact, its univariate Gaussian is extremely peaked. But f1 can't be that peaked because this mixture of two Gaussians is an isotropic position. So its variance as a mixture is 1. Its variance as a mixture on this direction is 1. So in fact, if this variance is very small in this direction, f1 has to be reasonably large variance. So in fact, f1, what we can do is we can construct an interval around f2 using our estimate f2 hat. And this interval doesn't need to be very wide to capture all of f2. It doesn't need to be very wide to capture all of f2, so that f2 is very unlikely to fall outside this interval. But because the interval is not that wide, and because f1 projected onto R is never that peaked, we know that not much of f1 falls into that interval. So in this case, we can make progress because we know our additive estimates aren't statistical estimates because they have a small variance. But we can cluster the data out so that we can cluster many samples with high probability based on which cluster generated them. Then we can just spit out the empirical mean and the empirical covariance. And those will be good statistical estimates of the two components. So now what we can do is the additive isotropic algorithm, well, it can feed into a clustering algorithm, which now, whenever you're given random samples from a mixture of two Gaussians, which is an isotropic position, well, you can always learn some estimate f hat, which is an epsilon close estimate, either way. And now we can fill in the rest of this, because what happens if you get a mixture of two Gaussians, which is epsilon statistically learnable, but is not in isotropic position? Well, the idea is simple. It's just if you're given such a mixture, which now is not in isotropic position, you can take many samples from it. And this actually you'll be able to approximate what transformation puts it exactly in isotropic position, because that'll just be taking the Cholesky decomposition of the covariance matrix of the samples. So what this means then is you can compute a transformation which has the property that it might not put the data into exactly isotropic position when it comes out, but what's true is that it's so close to being in isotropic position, meaning that there's another mixture of two Gaussians instead of f, which actually, according to this transformation t tilde, is exactly in isotropic position, that because our algorithm doesn't take many samples, our algorithm can't tell the difference. It can't tell that it's not in isotropic position. So in this way, we can fool the underlying algorithm, and this is the quickest and dirtiest way to finish up with this statement, is that now actually in the general case, we can learn a mixture of two Gaussians, even if it's not in isotropic position, if it's just epsilon statistically learnable. So are there any more questions before I get into the univariate? Nope. All right. So where are we? Right now, I've described the high-dimensional problem, and we've done all this work to reduce the problem down to one dimension. But now we're back at Pearson's problem. We have a mixture of two Gaussians in one dimension. How do we learn the parameters? Can we learn good additive estimates? So in fact, the first, we already know the answer. How many free parameters are there? There's only 5. So we've come a long way since Pearson's time. Now we'll call this an efficient algorithm, brute force search. Right, so we have 5 free parameters, and it turns out that each of them will be bounded because the entire mixture is still in isotropic position. None of them can be that large. But there's a catch here. It's not quite this simple. The real problem is, if we're saying that we're going to do some brute force search over this grid of parameters, we still need to devise a test for, first of all, telling whether the parameters are close enough. And the way that we're going to do this is actually back to Pearson's original approach. We're going to go through the method of moments. So we have this grid search over these 5 free parameters, and I claim that each of them is bounded because the entire mixture in one dimensions is in isotropic position, and each of the mixing weights is at least epsilon. So that means, for example, that, that none of the variances can be too large because the variance of the entire mixture is 1. So one of the variances can't be larger than 1 over epsilon because its mixing weight is epsilon. Similarly, the means can't be too large either because the mean of the entire mixture is 0. So if one of the means is too far out, then the variance of the mixture would be too large, again. So we've created this grid of parameters, and the idea we're going to use is very similar to Pearson's approach. We're going to compute the first 6 empirical moments based on taking a large number of samples. And what we're going to do is we're going to go over the entire grid, and we're going to accept if the possible candidate set of parameters that we're looking at, if its analytic predictions are close enough, for some notion of close enough, to the empirical estimates that we've observed, if they're close in the first 6. Now, the catch here is actually that what if I take my grid of parameters? What if my true set of parameters is here? Well, any way I reasonably define this test, certainly the closest grid point is going to pass the test. However I reasonably define this test, the real catch is how do I prove that there's no spurious set of parameters that somehow magically passes the test? What if this set of parameters has nothing to do with this? It's not close at all. How do we know that it's not close in the first 6 moments? Is that clear? All right, and so here's how we'll do it. We'll actually show it in the contrapositive. The idea is you want to assume that, say, f and f hat are different from each other. They're epsilon different. And this will be this notion of epsilon standard here. So first of all, the parameters in f and f hat both need to be bounded, because we're only considering, say, bounded solutions in the first place. Well, as I mentioned, each mixing weight is within epsilon and 1 minus epsilon, and the means and variances are all bounded. And additionally, we require that the parameter distance between f1 and f2 in each of these is also lower bounded, because in the univariate learning problems that we encounter, based on this isotropic projection lemma, f1 and f2 will have different parameters. And we assume the same thing for f1 hat and f2 hat. And additionally, we're going to say that they're epsilon standard or epsilon different if there's no pairing of their parameters, so that across this pairing they're close. So if there's no pairing pi, so that the mixing weights, the sum of the difference in the mixing weights and the parameter distance is too small. So the idea is we want to show a theorem of the following form. We want to show something to the effect of, if f and f hat are epsilon standard, which the intuition is that if they're epsilon standard, they're not good estimates for each other's parameters, because across this there's no pairing so that they're good estimates. So if they're epsilon standard, then one of the first 6 moments is non-negligibly different, is noticeably different. So one of the first 6 moments between f and f hat is different by some polynomial in epsilon. So what this means is if we had such a theorem, then our test would be well defined. Because all we would have to do is we'd have to take enough samples so that our empirical moments are close enough to the true grid point that we should accept, in terms of they're at least this fixed polynomial. And then this theorem tells us that any point that we find in the grid which actually is close enough on each of these first 6 moments, well, it has to be that the parameter distances are, that the parameters are close to the true underlying parameters. Is that clear? Question? Yep. Oh, no, go ahead.
So this power of epsilon will depend on k in general?
Yes, exactly. Exactly. And I'll show you some reason for why it depends on k. But even for the case of 2 Gaussians, the power is embarrassingly high, where there's no notion of k. This is where there was a 67 at some point. OK, so actually what I want to focus on right now is just, in order for this theorem even to be plausibly true, the first thing that we have to establish is that what if f and f hat were different? We didn't know anything about a lower bound and the difference in their parameters. What if they were just different mixtures of 2 Gaussians? At the very least, we would have to show that if there were different mixtures of 2 Gaussians, that one of their first 6 moments was different. Forget what that quantitative relationship is, that if they're epsilon different in parameters, that it's at least a polynomial in epsilon difference in their means. But actually, once we can show that different f and different f hat implies that one of the first 6 moments is different, it turns out there's actually a lot of intuition from things like algebraic geometry that this should actually be a polynomial relationship, and that's exactly what we prove here, but I'll get into that intuition a little bit later. So now I just want to show this weaker condition. Why is 6 the right answer for this? Why are, if you have 2 different mixtures of 2 Gaussians, why is 6 moments enough to distinguish between the 2, as opposed to, say, going out all the way into the tails to distinguish between the 2? So, suppose we have one mixture of 2 Gaussians depicted by this red mixture, and suppose we have another mixture of 2 Gaussians depicted by this blue mixture. So I can take the density functions of each of the 2 mixtures of 2 Gaussians. Those are just 2 different functions. And what if I form their pointwise difference? So I take the convex combination of these 2 red Gaussians, and I pointwise subtract that function from the convex combination of the 2 blue Gaussians. What I get is some function. And it crosses the 0 axis potentially. Let me assume for now that this function crosses the 0 axis at most 6 times, let's say. Suppose that were true, then the claim is we would actually be done with this weaker condition. Because in fact, what we could do is we could fit a polynomial to the sign difference. The degree of this polynomial is now at most 6. It's 6 in this case because it crosses the 0 axis 6 times. But this polynomial integrates to something non-zero against the difference between the 2 density functions. So that'll actually imply that one of the first 6 moments is different for these 2 Gaussians. So if we take the absolute value of the integral of p of x against f of x, which is the difference between the 2 density functions, then we can just expand this based on whatever the coefficients are for this polynomial p of x, and it's just the degree 6 polynomial. If we apply triangle inequality, then we're just going to factor out the absolute value of these coefficients. But the integral of x to the r against f of x is the difference in the two density functions. Well, the integral of x to the r against the difference in the density functions is the difference in the rth raw moments of the two mixtures of two Gaussians. So in fact, what this means then is that there is some r from 1 to 6, so that these two mixtures of two Gaussians have non-zero difference in their rth raw moment. So now, where are we? We've taken this high-dimensional learning problem. We've reduced it down to one-dimensional learning problems, which we've said we're going to solve via brute force. And somehow I claim that the heart of the matter is just, showing that 6 moments are enough. And now this problem is all the way reduced down to just this question. If we take one mixture of two Gaussians and we pointwise subtract another mixture of two Gaussians, how many times does it cross 0? That's it. That's the question right now. So we're actually going to prove this, that it crosses the 0 axis at most 6 times, based on the heat equation. So here's what we want to prove as a proposition. Suppose we take a linear combination of k Gaussians. So by linear combination, I mean these can be positive or negative coefficients. So in the case that we're most interested in right now, it's a linear combination of 4 Gaussians, because we're adding 2 Gaussians and subtracting 2 more. Well, so k is 4, and we want to show that f of x, if it's not identically 0, then it crosses 0 at most 2k minus 2 times, or 6 times in our case. And it's just going to come from this theorem, which is going to sound a little bit out of thin air, but I'll try and make this more intuitive, which is suppose we take some function f of x on the real line. If we convolve this function by a Gaussian, then the number of 0 crossings does not increase. And so this might seem a little bit out of thin air, but let me give some intuition for this. So convolving a function by a Gaussian is related to the heat equation. For example, if I took some function f of x, and I took that as the initial heat profile along the real line, and I asked the question, what does it look like at some later time? Well, the answer would be you convolve f of x by an appropriately chosen Gaussian, where the variance depends on how much time has passed. So since convolving by a Gaussian corresponds to this physical diffusion process, a lot of very intuitive properties, you would think are true and are, rigorously true if you go into the mathematics behind it. For example, diffusing some heat shouldn't intuitively create a new local maxima, because every time you create a new local maxima, the heat equation is immediately going to give you some diffusive pressure to try and suppress that local maxima. The same way a local minima, you can't create a new local minima because you're going to have a diffusive pressure to pull it back up. And that's the same reason, intuitively, that you can't increase the number of 0 crossings when you convolve by a function, since the number of 0 crossings and local maxima, at least, you should intuitively see are somewhat related. So now what we can do is we can just use this simple fact. Now, convolving 2 Gaussians by each other just adds their means and adds their variances. And now we can prove this proposition by induction, because we assume it's true for, k, let's say, equal to 3 for now. So if we take any linear combination of 3 Gaussians, it has at most 4 0 crossings. The point is, now if we take any linear combination of 4 Gaussians, what we can do is we can first subtract something from the variance of each of these Gaussians, the same quantity. Subtract the same value. We subtract the value so that the skinniest Gaussian becomes a delta function. So if we do that, we get this linear combination of Gaussians. And the point is, let's ignore the delta function for now. So what we have now is we have a linear combination of 3 Gaussians. So we know by induction that this function that we get when we add up the blues and subtract off the reds, what we get is this function, which crosses the 0 axis at most 4 times. But now when we add back in the delta function, we know exactly what happens to the number of 0 crossings. We add at most 2, because we'll add 1 on the way up and 1 on the way down. So in fact, this function that we get out here crosses the 0 axis at most 6 times. And now when we convolve by the original Gaussian, a Gaussian of that variance that we subtracted off, we get back as the original linear combination of 4 Gaussians. But convolving by a Gaussian doesn't increase the number of 0 crossings. So this linear combination also has at most 6 zero crossings. So any questions?
So in the formulas you described, you used zero-centered Gaussians, and in the
Right. So in general, if you convolve two Gaussians, you add the means and you add the variances.
oh, okay.
In any case, we only need this for convolving by Gaussians of 0 mean, because I'm just convolving by a Gaussian of the variance that I subtracted off, and I'm keeping the means the same for all the Gaussians.
Okay, I see.
But yep. Yep.
Well, what you need now is some quantitative estimate for the area between the...
Yeah, so it turns out, OK, so let me take a little detour, and I'll get more into this in some of the open questions session as well. So it turns out that really you can think of the method of moments as being really related to algebraic geometry. Because if you're trying to learn through the method of moments, well, asking the question, if you now have estimates for, let's say the exact values for what the rth raw moments were, asking what set of scalar values for the parameters of your mixture of Gaussians could possibly explain the data is asking, it's characterized by some system of polynomial equations. So in fact, asking that question is equivalent to saying what's a variety, right? It's, the set of all possible explanations for your data is a variety, because it's all the solutions to some system of polynomial equations. What I just did here was I proved for you that the zeros of this variety are exactly the set that we're interested in. That the only possible explanations for the exact right values for all of these first 6 moments is just the parameters of the actual mixture of two Gaussians, or the one where you say exchange which one's component 1 and which one's component 2. But then it turns out that there are things called like effective Voyashevich inequalities in algebraic geometry, which tell you that if the zeros of your variety are, say, at 2 locations, then if you're not at one of the zeros, so if you're epsilon different in one of the parameters, that one of those polynomial equations must be far from being satisfied by some polynomial in epsilon, where that polynomial just depends on the degree of the, it just depends on like the number of sort of polynomial equations and the number of variables and those types of things. So it'll give you this polynomial relationship between, if you want some additive accuracy epsilon, how much, if you're off by epsilon in the parameters, how much one of those, polynomial equations must be off some polynomial in that. So the way that we actually did it in the paper before we realized some of these connections was, actually based on these ideas. This idea of sort of deconvolving and subtracting something from the variance of the Gaussian was, as you were hinting at, was because what you can do is if you had some mixture of two Gaussians, another mixture of two Gaussians, and you wanted to distinguish between the two, well, here you look at the skinniest Gaussian, and there's no other Gaussian that really matches it. The point is what you can do is you can subtract something from the variance to isolate that Gaussian, and that'll be enough to sort of show that their moments are different between these two and get some quantitative difference. And then you can actually go through sort of the equations and relate the difference in the moments when you've subtracted something variance to the difference in the moments when you haven't. So you'll get like sort of recurrences for sort of Hermite polynomials out of this. But what that means is that if you have some non-zero difference in the moments when you've subtracted something off from the variances, you'll also get something maybe worse, but something different in the moments before you've subtracted something off. And this is also sort of why you get the k exponential in the exponent of even the univariate learning algorithm, is just because if I take linear combinations of, say, 2 times k Gaussians, I really am going to get that many zero crossings. 2 times k minus 2, 0 crossings. So you actually do need that many moments to even be able to, say, distinguish between the two, and that's why we end up getting that. I can tell you more about that later, too. It's a little bit sort of technical, so I didn't want to get into the proof of that theorem too much. Are there any other questions? So the last thing that I can show you is also I want to show you a little bit of the intuition for what happens for k Gaussians. So it turns out some slightly pathological things can happen when you consider mixtures of more than 2 Gaussians, which actually took us a little bit of time to sort of overcome. So here's a mixture of 3 Gaussians. It's epsilon statistically learnable. It's even in isotropic position. But now the real problem is that this isotropic projection lemma that I asserted for 2 Gaussians, well, the correct generalization to mixtures of more than 2 Gaussians isn't what you think. Because in fact, here, when we project onto a randomly chosen direction, say this direction, it's not the case that all pairs of univariate Gaussians in the projection have large pairwise parameter distance. Instead, these 2 Gaussians, in any way that you reasonably project it with high probability, will have very close parameter distance. And similarly, if we project onto this other direction S, somehow the correct generalization is not that over a randomly chosen direction R, for all I and j, they're different in their parameter distance. The correct generalization is that there's always a pair which has large parameter distance in some projection. Yep?
Could you perhaps try and do this by projecting onto a k-dimensional space and then solving the polynomial equations in k-dimension?
So I think you're on the right track. Let me rephrase that in a way, which is what you would actually want to do in this case is, these two could be exponentially close. So what you actually want to do in this case is you might want to learn a mixture of 2 Gaussians here. So you would learn this Gaussian and then just one which is additively close to both of these two. And you could keep doing this over all these directions. And maybe what you'd get is you'd get one Gaussian here and one very thin Gaussian here, which then is additively close to both of these 2 parameter sets. Of course, it has to have a very small variance because it can't be statistically close to both of them because they're not statistically close to each other. So the point is that then what you really want to do in this case is you want to learn a mixture of 2 Gaussians. And then when you realize that it's not a good statistical estimate because you have a small variance, you want to project on that direction and filter the mixture of Gaussians into smaller mixtures of Gaussians. So in this case, if you learned some estimate right here, then what you would do is you'd be able to filter out these 2 Gaussians from the base green Gaussian. And the intuition here is that you haven't chosen the right coordinate system to even be able to learn the difference between F2 and F3 right now. Because if you just ignored F1, then the mixture of just F2 and F3 is not in isotropic position. It's very far from it. The intuition is that isotropic position chooses the right way the right measure on the different directions to project so that you actually can see the difference. Because if I were to ignore this Gaussian, and then I then put this into isotropic position, just F2 and F3, what it would do is it would split F2 and F3 apart. And then I would be much more likely to choose something, a direction, which separates the 2. So in fact, so as I mentioned, the correct generalization is not that for all I and j, that the parameter distance is large. The correct generalization is that there is some pair which the parameter distance is large. And that'll tell you intuitively you'll always make progress because you'll always be separating at least 2 Gaussians from each other in this sort of hierarchical clustering approach to it. But there are going to be a few other problems that we encounter, and this I'm really just going to sketch at a high level. Oh, yeah. Oh, OK. So one of the biggest problems here will be, now.
Well, I guess you also need the same pair when you look at related directions. You get the same pair separated.
Yeah, so that's not too hard to show because you're going to choose the directions so close, and you're going to assume some separation between the different, you're going to learn some estimate which is close to some partition of the Gaussians, and they'll be far enough apart so that, if something jumps out of the cluster, it can't jump into a new cluster. So you'll always sort of make progress by seeing a new cluster, and then you can restart in those ways. But the bigger issue actually will be now what happens when, now we can't assume some lower bound on this. So potentially, how are we actually going to learn a mixture of 2 Gaussians in this case? We need it to be the case that these 2 are so statistically close to each other that our univariate learning algorithm might not be able to tell the difference between this just being a mixture of 2 Gaussians. So we either, the real intuition is that now each univariate algorithm is really characterized in some sense by a window of the parameter distances. Because, yes, I mean, the way I've described it so far in this 2 Gaussian case is it assumes a lower bound on all the pairwise parameter distances, and then it'll learn some estimate which is additively close to the true mixture of two Gaussians. But you know what? If it's a mixture of three Gaussians, and one of the pairs is extremely close to each other, is so close that our algorithm can't tell the difference, then our algorithm will learn some mixture of two Gaussians that's close to some partition of the mixture of three Gaussians. So the algorithm is really characterized by a window, because it assumes that either all parameter distances are, so it assumes all parameter distances are either smaller than some defined threshold so that it can't tell them apart from just being a single Gaussian, or they're at least non-negligibly large so that it actually can tell them apart and actually will learn some mixture of Gaussians that's consistent with that partition. So now at a high level we're going to encounter this problem that how do we know what the actual pairwise parameter distances are between all these different Gaussians? Intuitively it could be the case that some pairwise distance falls into this window and then messes up our algorithm. But how do we know that our algorithm has failed and hasn't returned a good estimate? Well, the idea is we can actually do many sort of disjoint windows and run our learning algorithm with these disjoint windows. So here intuitively we're running some algorithm which will return a good estimate as long as all the parameter distances are either smaller than this or larger than this, and it'll learn something that's consistent with a partition of the mixture of Gaussians. And the same for all these other windows. And the point is now there are only k-squared different possible parameter distances between different Gaussians. So if you look at them as sort of balls falling into these different windows and potentially messing up those algorithms, well, a majority of the algorithms are going to return correct estimates. So even though a priori you don't know how to tell that this algorithm has failed, you can get these algorithms to fail in a safe way because a majority of them are correct. And in fact, this being correct at learning some partition of the true mixture of Gaussians, it'll tell you that in fact it has to be in some sense consistent with the partition learned for some larger parameter set. This has to be sort of a refinement that it's learned of this partition. So what you can do is then you can find these like long chains to actually be able to find some good estimate among this set and actually be able to determine something that is consistent with the majority of the windows that you run the algorithm on. And so now then, as I mentioned, what you're at the end of the day going to do is you might learn a mixture of two Gaussians, one which is consistent with this green one and one which is additively close to these two. And you'll realize that the mixture, the Gaussian which is close to F2 and to F3 isn't statistically close to both of them, so it has to have some small variance. And in this case, you can then project the data onto that direction and make progress in this hierarchical clustering because you'll factor out F2 and F3 from F1. But now the point is once you have F2 and F3 factored out from the rest of the mixture, you can put these two into isotropic position, which is really like learning what are the right ways to stretch the data so that you can separate these two Gaussians from each other. So that's all I really wanted to say about that, since the proof gets a little bit technical. But are there any questions about this high-level proof? Yep.
So what I mean, here you've drawn the example, this fairly extreme case of extreme narrowness where you're gonna select these out. Is it not possible that you get this if sort of their joint thing is somewhat close to isotropic? I see. Yeah, I see.
So the key point is that actually this is the only way that it can happen, because at the end of the day, what you would learn in this case, if you learned a mixture of two Gaussians here, and you learned a mixture of two Gaussians there, which this mixture was consistent with the natural partition of this into a mixture of two Gaussians, well then you would have good additive estimates for this. You would have a mixture F1 hat and F2 hat, where F1 hat is close to F1, and F2 hat is additively close to both F2 and F3. That's what I mean by it's consistent with a partition. The only way that can happen is if there's a small variance, because there's no Gaussian F2 hat, which is statistically close to both F2 and F3, because they're not statistically close to each other, in fact. So that's the only way it can happen. And then the point is that you'll notice that because you'll have a small variance for F2 hat. So then you can actually cluster the data out and run this recursively, because then you can put F2 and F3 as just as a reweighted distribution into isotropic position and make progress in that way.
So the point is you'll detect that there are two clusters when you try to put that thing in isotropic.
Yeah, and exactly. And because of this isotropic projection lemma, this generalization, that there's always some pair that's separated, you'll know when you reach a termination condition, because if there's just one Gaussian left in this thing, then you can't see two different parameter distances between the two. So that gives you the termination condition on it. And actually, this even works in a more general context, because now, actually what you can do is you're actually in general given just an upper bound on the number of components. And this will just affect, if you're given k prime as an upper bound and k is the right answer, you'll be exponential in k prime, but you'll still work with that relaxed sort of guarantee. Because you need that when you sort of do this induction, because when I cluster out these two different sides from each other, I don't know how many Gaussians go to each side. All right, so now I can discuss the open questions a little bit, and that's really all I had planned, so tons of questions. So when does the method of moments provably work? So this was one example, but it's actually it's pretty characteristic of many different types of learning mixture problems, because here, in general, the method of moments, as long as the moment of a distribution is analytically some polynomial in the underlying parameters, then in fact the method of moments is really just asking a question about algebraic geometry. It's really saying that the set of possible candidate explanations is a variety, and understanding properties of this variety is very important to understanding when the method of moments works. The first thing that you need to establish is that the zeros of this set are exactly the ones that you're interested in. That if you learned the moments perfectly, then you actually would be learning the correct parameters. And yeah, so the hypothesis class is a variety. And we can even ask a stronger question, which was, I guess, a pipe dream of mine. I'm not sure it's really workable. But one could ask if computational algebra packages can help in designing algorithms. So now we're faced with an interesting question. So in the case of mixtures of Gaussians, we had to establish that 6 moments were the right answer. But in general, establishing that the zeros of a set of, that a variety is equal to another variety, which is maybe just the set of actual parameters, establishing that these two are equal in principle is doable by computer algebra packages. So one could imagine that you could have algorithm designers checking whether or not their system of moments actually uniquely defined the answer based on asking questions to algebraic geometry packages about the varieties that they're inducing. In fact, one could ask an even stronger question, which is in some cases you even have choices over which moments you want to use. So in this high-dimensional learning problem, as I mentioned, well, the way that I described it right now, and we project it onto some base direction, we project it onto many neighboring directions, well, we were essentially running the method of moments on those directions. Well, you have some freedom in actually how you choose those directions. So in the same way, you're really running the method of moments over a system of potential polynomial equations that you're generating based on the directions you're projecting on. So you could even ask, can you choose those more intelligently? Given some freedom of how to choose these polynomial equations, can you choose them in the best possible way to, say, minimize the number of polynomial equations that you need to uniquely define the system you're interested in, or maybe even to optimize more interesting things like this sort of polynomial condition number, which says that if you're epsilon different in the parameters, that what that polynomial will be in epsilon so that you can notice the difference. This, unfortunately, it seems, to the best of my knowledge, when I tried proving these things with computer algebra packages, even after we had the proof of this, they don't seem to terminate. So I don't know what one should do there. And in general, I think, oh, yep.
So the part where you use brute force search in your algorithm, could you replace that with a computer algebra procedure to solve it, or would this be safe?
Yeah, so I don't know of any provable guarantees for those types of things. I mean, there has to be sort of, if you want to talk empirically, there has to be a way to do that. But I'm not sure. I was more asking the question, now if you have some freedom and you're really setting up a system of polynomial equations, but you have freedom in which polynomials you choose based on, say, which directions you're projecting in, then how can you choose it so that even just brute force works the best as it can? so that you get the best polynomial relationship between the desired accuracy and how much one of the moments will be off for one of those equations.
So you're trying to run the computer algebra system.
Yeah, so these things all, what?
You're trying to run these systems to choose the direction.
Well, I mean, you're trying to run them to first see if the variety is exactly the one you're interested in. If using that set of moments, first of all, uniquely, tells you that the only possible hypotheses that explain your data perfectly are the actual things you're interested in. And then I don't even know what to do for optimizing that polynomial relationship, but this is even just working with the zeros perfectly. How do you do that? These things tend to run out of memory very quickly. And the problem is that if you truncate it to instead, in order to really compare varieties, you sort of need to use these, the radical of the ideal types of things. So you need to work over an algebraically closed field, which unfortunately then if you truncate it to being a finite field, if you magically get that these radicals of the ideals equal each other, that doesn't tell you that they're also equal over the complex numbers as well. So you're not sort of guaranteed that your answer really is the correct one. I mean, the way that you sort of compare varieties being equal is by taking the ideal of their variety and then comparing the two, and that's only, you only get this if and only if statement over algebraically closed fields. But what I think is also an interesting question in statistics in general is that here we're using dimension reduction to get around some sort of curse of dimensionality here. Instead of trying to figure out these n squared different parameters in high dimensional space and searching over all possible directions, we're reducing it down to one dimensional problem, which you can look at it as a form of just dimension reduction, which we as computer scientists are very good at. And from talking to statisticians, a lot of times statisticians love maximum likelihood estimators. So in fact, they can oftentimes prove that maximum likelihood estimators converge quickly, maybe under some assumptions about the Fisher information. But when you're proving that maximum likelihood estimators converge quickly, you're presupposing that you can compute the maximum likelihood estimate efficiently. Actually, for mixtures of Gaussians, it's NP hard. This is in the work of Aurora and Kanan. It's NP hard to compute the maximum likelihood estimate. It's in fact even APX hard. So one could ask, how do you get around these types of problems? And in general, perhaps there are estimators which can be coupled to maximum likelihood, so they're not exactly maximum likelihood, but you can update things like the maximum, whatever the maximum likelihood is in your hypothesis class more efficiently than just sort of a brute force search over the entire space, and maybe you can do such things through dimension reduction, in fact. Yep. Okay, so I guess that's all I had. So thanks.
So in this isotropic projection lemma, you kind of